Hello. We're going to talk about distributed filter design using the Filter Solutions design environment. We'll start with a default design panel setup, with the exception that I have chosen Chebyshev 1 filter, distributed filter, and first element shunt filter. As you can see down here, we can set our substrate up, 1.27 millimeter dielectric height default, microstrip, alumina substrate with gold conductor, and alumina loss tangent. Our geometry selection, we selected to limit our line widths to 50 micrometers and our gaps to 500 nanometers. Let's pick 50 micrometers minimum gap as well. Let's go back to topology. Default values, 50 ohm terminations. We will let Filter Solutions calculate the quarter length frequency, which the default will be twice the cutoff frequency. Synthesize. And there's our filter. This is the schematic view. We have all of our widths and lengths. Looks like we got lucky. Nobody is up against the minimum width of 50 microns. This is our layout view. We can see what it looks like. We can see what our total width and total height of our filter is. If we go back to our topology page, we can see several other options. If we want to keep our capacitors and just translate our inductors to microstrips, this option is sufficient. Capacitors, microstrip inductors. And of course, we have our stepped impedance. First segment is fat. First segment fat, thin, fat, thin. Want to see our schematic? Again, everybody is wider than the minimum width of 50 microns. We want to see our analysis of this filter. We have lots of analysis buttons over here. We'll pick our S parameters. And now we have S11, S12 of this filter over here. S12, 21, S11, 22. If we want to design a bandpass filter, here is a classical translation, or excuse me, here is a lump translation of a classical lumped bandpass filter. And you can see we have some rather extreme widths in this filter, very wide widths, and here we are up against our minimum width of 50 microns. Our S parameters do look okay, but the nice thing about bandpass filters is we have many other options to pick from. We have the inductor translations, which we have already talked about. Shunt stub resonators. Here again, these are a little bit on the fat side. Equal stub widths. Chebyshev and Butterworth filters, we can make all these stubs the same width. Parallel edge coupled. You can see the total widths and heights of each filter. This has a tapped termination. Here's our pinned termination. It's a little bit narrower, but we also have fatter end segments. You can see the total height is very small in this case. And of course we can go on. We have hairpin, interdigital, and comb line. We can look at a hairpin. And you can see our S parameters are all still very nice, what we would expect. We have very little injection loss, about 1 dB. Zoom in on this a little bit better. Let's go with 500 to 2 gigahertz. So there we go, we can see a little better. Get rid of S11. We can use our left mouse key to see how accurate we got. 910. to 1.1. So we got a very good, accurate hairpin filter based on our own internal circuits analysis. If we want to check the accuracy of this against other software, we have lots of ways to export. We have Sonnet. The layout can be exported into DXF format files, and of course we have AWR. Let's look at our AWR export. It's our AWR export panel. We simply fill it out the way we would like, select append or overwrite to AWR, and now we have the entire filter exported into AWR. If we wish to do a electromagnetic analysis, export directly to Sonnet. There's our filter in Sonnet. And of course, Sonnet can very quickly and easily do a electromagnetic analysis. Okay, and it's done. Delete this page. Now we can look at our frequency response. Pull up S21. Now this graph is in a geometric frequency scale, log scale. Let's make it an arithmetic log scale so that we can match it up to Sonnet. And there we have it. This concludes our discussion of distributed design in the Filter Solutions design environment. Thank you.